Okay. So I just repeat because I forgot to record the starting part of the lesson. Yesterday, while calculating the energy density of the level, I forgot the two prefactor in front of the summation and in front of the integral. So if we consider also these two prefactor, then we have the energy density equal to 3 divided by 2 electronic density divided by Fermi energy times the ratio of the energy to the Fermi energy to the power of 1/2. This describes how the number of levels increases as the energy the value of the energy increases. Yesterday, when I made the calculation, at some point, when I switched from Cartesian coordinates to spherical coordinates, and I made the integration over the angular variables, I, at the end, had an integral where I wrote 0 and kf as limits of integration. And that was to take into consideration the fact that only the levels, that the occupied levels are only the levels that are included in the Fermi sphere. Now, this is just, let's say, my assumption. So yesterday, the idea was just to evaluate the energy density. So at the end, the limit of the integral are not important because the aim of the calculation was not to evaluate something specific, but was just to show you that with the change of coordinates, it's possible to define G of V. The idea is when we in the future, buongiorno, when we in the future will make integrals where we evaluate the energy, whatever, depending on the electronic levels, the idea is not to take into consideration the occupation, or as in this case, the value of kf through the limit of integration, but to take into consideration the occupied levels through the equilibrium distribution function of the electrons. So from now on, we will refer to the Fermi Dirac distribution function, that is the equilibrium distribution function that describes the occupation of the levels of the electrons in this model and in all the models that we will use from now on. The Fermi the Fermi-Dirac distribution function depends on the wave vector of the electron, but depends on the wave vector thanks to the energy. So the wave vector dependence is through E. So the energy depends on the wave vector. So F is in principle a function of the wave vector, but that dependence is just through the energy. Here we have the energy of the electron, the chemical potential, K is the Boltzmann constant, and T is the temperature. Yesterday, what is the shape of this function? If we make a plot of F as a function of E, if when T is equal to 0, so when the temperature is set to 0 Kelvin, the Fermi-Dirac distribution function is just a step function. So it is 1 up to the chemical potential, and then the value drops to 0. Yesterday, we showed that this behavior, when we occupy the electronic levels and we fill all possible levels, we end up with the sphere that is completely filled, and the maximum energy that is occupied by the electron in that sphere is the Fermi energy. So due to this diagram, we may say that the T equal to 0, the chemical potential equals the Fermi energy. So this is EF. What happens when we increase the temperature? When the temperature is increased, this is no more a step function. So we have a change from 1 to 0 that is smoother than that. And we have something like this. And as the temperature increases, then the deviation from a step function is more and more pronounced. And just to understand what does the deviation from a step function is more and more pronounced as we increase the energy, as we increase the temperature, let's just see how the width of the region where the function is not 1 nor and is not 0 compares with the thermal energy. So in general, it can be shown that let's say the range of energies where the function moves from 1 to 0 is of the order of kBt. So the interval where the function starts from 1 and drops then to 0 when t is different from 0 is of the order of kt. If, for instance, we fix t equal 300 Kelvin, just to make an evaluation, we have that kBt is of the order of 0.025 eV, just to have an estimate of, let's say, the width of the range where we have this change from 1 to 0 concerning the occupancy, the average occupancy of the levels. Now, what is the, let's say, what is the value of EF? EF is equal to h bar squared kF squared divided by twice the mass of the electron. Kf is related to the density of to the electronic density, and yesterday we saw that Kf is of the order of 10 to the 9 meters to the minus 1. So if we use the value of h bar squared, we use the value of Kf that we evaluated yesterday, we set the mass of the electron to the rest value, we have that this number here is something that over all the metals that we have in the periodic table ranges from 1.5 up to 15 eV. So it's not a fixed value, but it's something of the order of some eV, more or less. This value here is larger and larger with respect to the thermal energy. So this means that if you make a plot in scale, so if you put in the same scale the Fermi energy and the thermal energy is very, very small with respect to the Fermi energy. So even when we are at room temperature, the deviation of the Fermi Dirac distribution from a step function is really negligible. So you have just a small change of the occupancy very close to EF. So the plot that I made before is not in scale because the range of variation is very large with respect to EF in my plot. So the actual result is that the deviation is just observed very, very close to EF. Due to that, and just to conclude this comment, when do we expect to see something, a variation like the one that I plot here? So when do we expect that the Fermi energy is strongly different with respect to a step function? At this point, if we want to observe a strong modification of the Fermi Dirac distribution, we have to set the temperature to a value such that the thermal energy is comparable to the Fermi energy. So in that way, we have a strong modification of the shape of the function. To have that, what is generally found is to define kBTF, that is, let's say, the Fermi temperature, that is the temperature, let's say, it's a measure of the energy, not in eV, but in Kelvin. And this can be done just by dividing or multiplying by the Boltzmann constant. In this case, what is found is that the TF is of the order of 10 to the 4 or 10 to the 5 Kelvin. This means a huge temperature. So we will never have the opportunity to study a metal at the temperature of 10 to the 4 Kelvin, because at that temperature, for sure the metal is melt or even evaporated. So we have no metallic state in this condition. So the idea is that it's impossible, let's say, in normal conditions, to observe a Fermi-Dirac distribution that is very different from a step function. So in general, let's say the actual structure of the Fermi-Dirac distribution will not be a step function when t is different from 0, but in many cases we can use the idea that the Fermi-Dirac is nearly a step function, due to the fact that to distort the dependence of the Fermi-Dirac distribution with respect to a step function, we need a very, very large temperature. And that temperature is not met in usual experiments. So that's why, for many cases, the dependence will be very, very close to the dependence that we have for a step function. So in general, the correct way to write this this summation. So if we want to calculate something like this, so the summation of F, where F is the energy, the velocity, whatever we need to use to describe the electrons, then we use the same method described yesterday. So volume element divided by the density of levels, so to find the number of electrons, the two factor to include for spin up and spin down electrons, then f of k, that is the function that we want to evaluate, and Fermi-Dirac distribution. So thanks to the presence of this function, where f of k is f of E of k, so the dependence on k is just through the energy. This f of k, what is the role of f of k? When I make the change of variables, as I did yesterday, from Cartesian coordinates to spherical coordinates, as E as spherical symmetry, then f of k replaces the upper boundary of the integral. So at that point, I just make when we have the integral in decay, where k is the modulus of the wave vector, here we set the limits from 0 to infinity. So all possible k values, k moduli in this case. But we have here f of k. And f of k is what replaces the upper boundary that I said yesterday. Yesterday, I said that the upper value of k was kf. So I was implicitly saying, let's just sum up the electronic levels from 0 to kf, because I suppose that the temperature is equal to 0, so the Fermi distribution is a step function. No occupied levels at energies higher than EF. But if the temperature is different from 0, I may not assume that, because I have electronic levels that are occupied also for energies higher than EF. So here I may not fix a precise value of the energy. Sorry, I may not fix a precise value for the modulus of k. So I just include in the integral f of k, that is the weight that tells me how many occupied levels I have for a fixed value of k. So this allows me to count all the possible electrons that occupy levels within the system. So in general, when we will try to evaluate some quantities, we will introduce the Fermi-Dirac distribution that accounts for the occupied levels. Okay, and just two last details before going on. First, I would like to evaluate the, I think you have already calculated that, but it's just, I would like to recall that just to make a comment on the value that we will obtain. In the Drude model, the average energy of the electrons was given by the Maxwell-Boltzmann distribution and was proportional to kT. Now, in this case, what is the average value of the energy? So the idea now is to evaluate the average. the average electron energy. Just to make a simple calculation, I will make the calculation at T equal to 0 Kelvin, but I do that just because in this way I may forget to include the Fermi-Dirac distribution, or in other words, I may consider the Fermi-Dirac distribution to be a step function. So it's just for simplicity. But as we saw before, due to the fact that deviation of the Fermi-Dirac distribution from a step function is not very pronounced, even at room temperature, I for sure make a mistake in supposing that the temperature is equal to 0. But let's say the mistake that I make in the calculation is very, very small. So that doesn't affect the order of magnitude of the average energy. Due to that, if I want to obtain the average energy per electron, I evaluate the total energy of the electronic system and I divide by the number of electrons. So in this way, I have the average energy per electron. Yesterday we saw that we may evaluate this parameter using G of E. So in this case, I can use G of E So I set the electronic level energy density. E in this case is the equivalent of F. So the function f of E that I used yesterday in this case is just equal to E because I'm trying to evaluate the average energy. And if you, let's say, if you remember yesterday, there was a volume factor out of the integral, and that volume was there thanks to the 2 pi to the power of 3 divided by V, that is the volume of one level. So I just include that volume here. And so we have that in this case, what is the limit of integration? If I supposed to be at t equal to 0, the upper limit of the integral is EF, because there are no occupied levels at energies higher than EF. So this is the integral from 0 to EF. G of V is 3 divided by 2 electronic density divided by EF times energy divided by Fermi energy to the power of 1/2 times E dE. Sorry. And then I have to divide by the number of electrons because I want to have the average energy per electron. Here I have electronic density. If I multiply the electronic density by the volume, I have the number of electrons. Due to the fact that I divide by the number of electrons, the number of electrons disappears because I have that at the numerator and the denominator. So here I'm just left with 3 divided by 2, 1 divided by EF, and EF is to the power of 3 divided by 2 because I have one EF here and another EF within the parentheses. And then integral from 0 to EF of the energy to the power of 3 divided by 2 times dE. So this is 3 divided by 2, 1 divided by EF to the power of 3 divided by 2. Then the integral is E to the power of 5 divided by 2 divided by 5 divided by 2 evaluated from 0 to EF. So I'm left with this result. So here I may simplify this 2 factor. 5 divided by 2 minus 3 divided by 2 is just 1. So this is equal to 3 divided by 5 EF. So the average energy per electron is nearly equal to EF. I've just a 3 divided by 5 factor, so the order of magnitude is the same. This value, so this is the average energy for the Sommerfeld model, that is larger and larger with respect to the average energy that was 3 divided by 2 times Boltzmann constant temperature. That was the average energy for the Drude model. So just by the only difference here is not due to the let's say hypothesis of the model, because the hypothesis was exactly the same, but it's just to the way we used to handle the electrons. Drude handled the electrons as classical particles. Sommerfeld handles the electrons as fermions, so particles that are described by the Fermi-Dirac distribution. So what is the physical motivation behind this huge difference? What is the physical motivation that brings about an average energy now that is at least 2 orders of magnitude larger than the average energy for the Drude model? So why in the Drude case the energy was so low, and why now the energy is so high? Yeah, in the Drude case, in principle, all the electrons may have exactly the same energy, same level, may do exactly the same things. Now, the Pauli exclusion principle forbids the electron to stay in the same state, to occupy the same level. Just 2 electrons may occupy 1 level. So due to that, the fact that let's say, if we start to fill the electronic levels with electrons, as soon as we put 2 electrons in 1 level, that level is forbidden for all the other electrons. So the other electrons has to occupy other levels, and so on as we increase the number of electrons that we put in the system. So somehow, and please consider what I'm going to say not as, let's say, I don't know how to translate in English, prendete con le pinze, but please do not consider what I'm going to say as a strict and perfectly correct sentence. The Pauli exclusion principle, even if the model expects that the electrons are independent, the Pauli exclusion principle is a way to let the electrons depend on each other. Because if one electron occupies a level, then just one electron can go in the same level, and then no other electrons may occupy the same level. So somehow there is a sort of interaction between the electrons, and the interaction is through the Pauli exclusion principle, because again, occupied levels are, let's say, just 2 electrons may occupy 1 level. So this is a sort of interaction because all the other electrons may not stay in the same level. So it is not an interaction in the Coulomb sense. So we have not the Coulombian repulsion between electrons. That is not considered in this calculation. But the Pauli exclusion principle is a sort of way to say that there is actually an interaction between the electrons, because the choice of the levels cannot be done without considering the actually occupied levels, because only 3 levels can be useful to host an additional electron that is included in the system. And this is very, 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 very important. So we will see that the Pauli exclusion principle and the fact that the electronic energy, that the electronic levels build up the Fermi sphere is of huge importance in describing the properties of the solid. So we will see that using different models and evaluating different quantities, but that is really important. And the effect of the Pauli exclusion principle is to increase in this way the average energy of the electron. So nearly let's say 2 orders of magnitude larger in the Sommerfeld case, and of the order of 0.025 eV in the case of the Drude model. So this is due to Pauli exclusion principle. Okay. What I would like to do, now, one of the things that I would like to discuss with you refers to the capability of the system to conduct charges. So at some point in a while, I'm going to discuss with you what happens to the conductivity of the system considering the Sommerfeld model. Before doing that, let's just see what happens when we consider the velocity of the electrons that will then be used to describe the conductivity of the system when the electronic system is at equilibrium. So if we suppose that no external field is applied, so the system is in perfect equilibrium described by the Fermi-Dirac distribution, what happens to the velocity of the electrons? The velocity, I change it. Yep. We saw that the velocity of the electron, or momentum P, is equal to h bar k. Just a comment. P is a vector actually, K is a vector actually. So in principle, I should write the vector sign nearly everywhere. So let's say in general, I skip that, but it's not because I think that those are scalar quantities, but just is because sometimes I forget to always put the vector sign. So please consider that even if I don't put the vector sign here, P and K are actually vectorial quantities. So this is the M time V. So at first, we may see what happens when K is equal to Kf. So what is the velocity of one electron that is exactly at the Fermi energy? In this case, so we have the Fermi velocity that is equal to h bar Kf divided by the electronic mass. If you put here the value of Kf that we used yesterday, the electronic mass, you see that this is something of the order of 10 to the 6 meters per second. So with respect to the Drude value that was 10 to the 5 meters per second, here we have a velocity that is slightly larger, 1 order of magnitude. So this is nearly 1% of c, of the speed of light. So the average velocity, in this case, of one electron at the Fermi energy, is 1%, nearly 1% of the speed of light. What do we expect about the value of the average velocity of the system when the system is at equilibrium? I just would like to recall the diagram that we saw yesterday. Yesterday, we saw that when, sorry, this is not actually a sphere. So yesterday, we saw that if T is equal to 0, and more or less the same situation is observed when T is different from 0, the electrons, the electronic level, are found within a sphere, and the radius of that sphere is equal to Kf. As the velocity is equal to h bar k, this means that the velocity has the same direction of the wave vector. So if I choose as random one electron here, for instance, then the k of that electron, so this is the k that identifies the specific level, as the velocity has to be parallel to k, this means that if we plot the velocity, that will be along the same direction. So the actual velocity of the electron will be parallel to that vector. If now I consider that the occupancy of the level has a spherical symmetry, this means that if I pick up at random one electron in one point of the sphere, for sure there will be another electron on the opposite side of the sphere. So what I expect is that the average velocity of the system in this situation is equal to 0, because for any electron that goes in one direction, I have another electron for sure that goes in the opposite direction with the same modulus of the velocity. So due to the occupancy of the levels, what I expect is that the average value of the velocity when the system is perfectly at equilibrium will be equal to 0, as is expected, because in general, you do not observe that you have a flow of current or of charge of something in a metal that is at the equilibrium. So this starting point is similar to the starting point that we have in the Drude case. So also in that situation, the average velocity without external fields is equal to 0. Now the question is, what happens when I apply an external field? When we apply an external field, what happens? In principle, as Sommerfeld thought that the electrons had to be handled in a quantum mechanical way, one may expect that also the effect of the external fields should be handled, let's say, quantum mechanically. So one expects that maybe we have to put into the Schrödinger equation something that takes into consideration the external electric field, magnetic field, whatever. But at that point, the idea was that only the distribution function of the electrons was quantum mechanical in origin. So the electrons are fermions that have to follow the Pauli exclusion principle, so we need to use the Fermi-Dirac distribution. But for what concerns everything else, in particular the dynamics, the idea was just to follow what Drude decided to use, so second law of dynamics. So the idea is that also in this case, we have to refer to the second law of dynamics to see what happens when we apply an external field to the electron. So also in this case, we have to refer to the effect of the external force over the electron. Concerning the approach to obtain the conductivity of the system, I would like to use now an approach that is slightly different from the one that I used in the Drude case. And this is an approach that we will use again also with other models to evaluate again the conductivity. This approach uses a different method to access all the quantities of the system, because in the Drude picture, the idea was I have a point particle with the given mass. I know that there is a force applied to that particle, so I would like to see what happens to that particle thanks to the external force. So I write down the equation of motion, find the velocity, acceleration, and so on, and then evaluate all the quantities. And this is the classical approach. Another approach is the following. If I consider the system at equilibrium, the system at equilibrium is described by the Fermi-Dirac distribution function. When the system is out of equilibrium, because for instance, I apply an external electric field to observe the conductivity of the system, the distribution function has to change. Why does that has to happen? Because, for instance, if the distribution function would be always the Fermi-Dirac distribution function at the equilibrium, the velocity should be always equal to 0. So what one expects is that if something from outside the system is applied to this system, then that has to affect the distribution function. So F has to change some way to consider the contribution of this external perturbation. So the idea is if F of E is the equilibrium distribution function that I find when no external fields are applied to the system, then there has to be, I call that, say, if you don't mind, just in this situation, to state that f of e, the Fermi-Dirac distribution function, is the equilibrium one, I just put 0 as a label to say f0, f at equilibrium. I expect there will be an f of e without 0 label that is not the equilibrium, but is the distribution is the out of equilibrium distribution function. So f of e represents the effect of the external field, not through the equation of motion, but through the distortion of the equilibrium through the distortion of the distribution function that is produced by the applied external field. Just to make an example that is easy to plot in this diagram, please take this just an example of what may happen, not what actually happens. At the moment, I'm not able to plot exactly what happens. We will be later on. I will plot it in the next weeks. I will plot exactly what happens to the distribution function. But for the moment, please take this that I'm going to describe now, just an example. So if this is the Fermi-Dirac distribution at the equilibrium, now I exaggerate what may happen. And in this case, the velocity is equal to 0. What is a way to produce an average velocity that is not 0? What may I do? I may do a translation. So if I make a translation of the sphere, let's suppose that the translation is like this, and now I exaggerate. So if there is a translation of the sphere, then this means that the occupancy of the levels is no more spherically symmetric. And if the occupancy is no more spherically symmetric, then the average velocity will be different from 0. So this is what may happen to the distribution function to account for the action of an external field. So f in this picture is this distribution function. F0 is this distribution function. So in one case, the occupancy is the Fermi sphere. In the other case, again, a sphere with just a translation along the x-axis or another axis. So the idea is to go through this method, as this method is more general with respect to the method based on just the equation of motion, the solution of the equation of motion. How is it possible to handle and then to use this, let's say, new value of the distribution function to evaluate conductivity, density current, and so on? We may use the same expression that was used by Drude. In the Drude case, the density current was equal to minus E n times V. Now, we may just rewrite exactly the same thing using the Sommerfeld approach. In the Sommerfeld case, we have that J is minus E because, again, we have electrons. At this point, I have to sum up all the velocities, considering the fact that each electron occupies a level that is indexed by k. So again, I need to make an integral, the two factor to account for the spin up and down. Then I have d3k divided by the so what is the meaning of what I have included in this box? D3k is the volume element. 2 pi to the power of 3 divided by the volume is the volume of one level. So this ratio is equal to the number of electrons, sorry, is the number of electronic levels that I have in that D3k volume. I would like to have the density, not the number. So I should divide by the volume. So here I put 1 divided by the volume to account for the fact that that ratio is the number, and then I divide by the volume to have the density. Then I need the velocity. The velocity of one electron is h bar k divided by the mass. So here I set h bar k divided by the mass. So this is the, let's say, the equivalent of the Drude expression for the velocity of the electrons that considers the fact that the velocity of the electron, the velocity of each electron depends on the occupied level. The levels are indexed by k, so we sum up over all possible levels. What is missing here is the distribution function. So we also need the f of k, where if f of k is f0, that is the equilibrium distribution function, so we expect that this integral is equal to 0. If something modifies f0 and turns f0 into f, then I put here f, and I hope that the deviation of f with respect to the equilibrium value may produce a velocity that is different from 0. So at this point, the problem is, how is it possible to evaluate f? Because if we know f, we may evaluate the integral, calculate the density current, and we may expect, as in the case of Drude, to obtain the connection between the density current and the electric field, so to obtain the conductivity. And yeah, since it's nearly 10 o'clock, I would prefer to make the break now, so then I have the full hour to make all the details of to evaluate that. So if you don't mind, I make the break now, and then we will go on with the rest of the calculation.